Today we're starting a unit where we are going to be writing complex numbers in trigonometric form, polar form, in order to do stuff with them, okay? We can do things with complex numbers in polar form, trig form, that we could not do without that, all right? So first of all, let's do a brief review of our complex number unit, day, whatever, from last semester. The imaginary unit I is defined by the square root of -1. The complex number, a complex number in standard form, is written in as a plus bi, where a and b are real numbers. The real number a is called the real part of the complex number. The real number b is called the imaginary part of the complex number. A number of the form bi with no a, with no number being added, is where b is not 0, is called a pure imaginary number. The set of real numbers is a subset of the set of complex numbers, and that is true because every real number a can be written as a complex number using b equals 0. Okay, so if I say 7, that is a real number, but it is also a complex number if we think of it as 7 plus 0i. Okay? All right. We graph complex numbers on the complex plane. The y-axis is the imaginary axis in the complex plane. The x-axis is the real axis on the complex plane. So let's do a couple of these. We want to graph -5 plus 8i. That is just a point. Remember, that is just a point, just like the point 3, 4 is a point. This is a point on the complex plane. We go -5 on the real axis, and then we go to positive 8i on the imaginary axis. So -5, 8i would be right here. The point -7i. -7i is 0 on the real axis and -7i on the imaginary axis. So that would be that point. Okay. Let's graph 8 plus 6i on this complex plane. So I would go 8 on the real axis, and then 6i on the imaginary axis. Let's find the distance now between the origin and that point. So we're finding this distance right here. Okay, to find that distance, we can just use the Pythagorean theorem. This leg is of length 8, this length is of length 6. So this, using the Pythagorean theorem, would be the square root of 8 squared plus 6 squared. So that would be the square root of 64 plus 36, which is the square root of 100, or 10. This distance is called the absolute value, or magnitude, of 8 plus 6i. Okay? So we will denote it just like we do with any absolute value. Okay? All right. The absolute value of a complex number, a plus bi, is defined as the distance between the origin and the point AB. The absolute value of the complex number, z is equal to a plus bi, is the square root of a squared plus b squared. Okay, that absolute value is also called the modulus. All right, let's determine the absolute value of z if z is equal to this point. So the absolute value of z would be the square root of -6 squared plus 4 squared. That is the the square root of 36 plus 16, which is the square root of 52. And to clean that up just a hair, I can take a 4 out as a 2. And that would leave me 13. So 2 square root of 13. Okay, Last semester we learned how to add, subtract, multiply, and divide complex numbers. So let's do a quick review of that. I would add the real parts, and I would add the imaginary parts. And that's how we add those two complex numbers. To subtract, I'm going to first rewrite this as negative 6 plus 2i minus 5 plus 6i, distributing that minus through, and then I will add the real parts and the imaginary parts to get that sum. Okay, when we multiply, I'm just going to FOIL this out just like we always have. 3 times negative 2 is negative 6. 3 times 6i is 18i. Negative 5i times negative 2 is positive 10i. And negative 5i times 6i is negative 30i squared. I squared is negative 1 because the square root of negative 1 is I. Okay? So this becomes negative 6 plus 28i plus 30, right? That'll be plus 30. And then we have 24 plus 28i. Okay? To divide complex numbers, we are going to multiply by the conjugate of the denominator. And FOIL, FOIL, FOIL. Distribute, distribute, distribute. Negative 4 times 1 is negative 4. Negative 4 times 5i is negative 20i. 3i times 1 is 3i. 3i times 5i is plus 15i squared. But because of that I squared, that's going to make that a negative 15. On the bottom, we have 1. The middle term will zero out because we're multiplying by a conjugate. So at the end, we'll have a minus 25i squared. But because of the I squared, that will become a plus 25. So this will be negative 4 minus 15 is negative 19 minus 17i divided by 1 plus 25 is 26. So written in standard form, that would be negative 19 over 26 minus 17 over 26i. That is A plus BI form. A is negative 19 over 26. B is negative 17 over 26. Okay, what if we were asked to find the value of negative 2 plus 4i all to the 6th power? Well, we could use Pascal's triangle, or we could write this out 6 times and FOIL, 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 FOIL. Okay, either way, it would be a long process of changing i's and I squareds and I cubes and I to the 4th and all of that back into regular numbers or i's. It would be a process. What if we were asked to find this 5th root of this? How would we write that with no I under the root? How would we write that? Well, for powers and roots of complex numbers, it is very helpful to write complex numbers in trigonometric form. Okay, this is what we're going to be doing the rest of this unit. Okay, so what was that? Okay, 9 minutes of review. Perfect. Okay. All right, so let's use our knowledge of trigonometry. Okay, so this point right here, which is A plus BI, we're going to change to trig form. We're going to change that to trig form. Okay, all right. So I know that this length is A, this length is B. Here's R, and here's theta. This should look very familiar to you. We've done things very, very similar to this. Cosine of theta is adjacent over hypotenuse, that is A over R. So A is equal to R cosine theta. We did the same thing with polars, and where A was just an X and B was Y. Okay. Sine of theta is opposite over hypotenuse, B over R. So B is equal to R sine of theta. So substituting in place of A, I'm going to write R cosine theta. In place of B, I'm going to write R sine theta. And then we have that I in the back. Okay? I'm going to factor an R out and write this as R times cosine plus, and then I'm going to move this I to the front of the parentheses, I sine theta. I took out the R, right? Factored out the R. Okay, this is trig form of a complex number. Also called polar form. They're interchangeable. It's also called polar form. Okay. R is the distance from the origin to your point, so that is the modulus, square root of a squared plus b squared. And tangent of theta is b over a, opposite over adjacent, so b over a. Okay? All right. So that's what all of this says in this box. R is also called the modulus of the number, and theta is called the argument of the number. Okay? So we have this, and we are going to be writing this a lot. The whole rest of the unit, we're going to be writing that. An abbreviation for that, an abbreviation for this is cis, R cis theta. C is cosine, I is I, S is sine. So when you see R cis theta, it means R cosine theta plus I sine theta. It's just an abbreviation. So let's do a couple of examples here. Let's write this trig form of a complex number in standard form. So I want to change that to a plus bi form. Okay, well, that is extremely easy to do. We just go ahead and find the cosine and sine of these angles. Cosine of pi over 6 is square root 3 over 2. Sine of pi over 6 is a half. I'm going to multiply through by the 8, and I get 4 square root 3 plus, and then in standard form we put the number first in front of the I, so I'm moving the I to the back. Half of 8 is 4. So this would be standard form for this polar form. Let's do another one. Okay, 5 pi over 4. That is 5 times cosine of 5 pi over 4, which is negative square root 2 over 2, plus I times sine of 5 pi over 4. That is also a negative square root 2 over 2. Don't forget your I back in the back. And now to get it in standard form, that is a plus bi. I'm just going to distribute my 5 through, and I get negative 5 square root 2 over 2 minus 5 square root 2 over 2i. That is standard form. Okay, let's write this number in trig form. So to write that number in trig form, first I'm going to be thinking of where that is located. Okay, I need to know where my theta is. So where is this located? That is located negative 3 plus 3i, so negative 3 on the real axis plus 3i on the imaginary axis. So that's that point. Okay, so I need to get r, which is the modulus, right? So r is equal to the square root of the square of negative 3 is 9. The square of positive 3 is also 9. So r is the square root of 18, which is 3 square root of 2. That's r. Now to get theta. Well, in this problem, the magnitude of a and b happens to be the same. And if that's the case, I know that this is a pi over 4 angle in quadrant 2. So I know that that is theta is equal to 3 pi over 4. So I know that my trig form of this number is 3 square root of 2 cis 3 pi over 4. If you prefer to write out cosine of 3 pi over 4 plus I sine of 3 pi over 4, you are welcome to. I will quite likely be using the abbreviation form. Okay. However, if, well, let's do this one. Okay. So for this one, what quadrant are we in? We are in, the real part is negative, the imaginary part is negative, so we are down here in quadrant 3. And this time the magnitude of A is not equal to the magnitude of B, so we'll have to do something else to get there. Alright, but let's start with R first. R is the square root of the square of A plus the square of B, that is the square root of 12, or 2 square root of 3. Okay. Now for theta. Since I don't know, since the magnitude of these are not the same, it's not a pi over 4 angle, I know that, I'm going to use tangent of theta is B over A. B over A. So tangent of theta is negative 3 over negative square root 3. Okay. I'm going to rationalize. And when I rationalize, I get tangent of theta is positive 3 square root 3 divided by 3. The 3's reduce out, and I get tangent of theta is square root of 3. That means that this is the pi over 3 angle. Pi over 3 angle in quadrant 3. And the pi over 3 angle in quadrant 3 is 4 pi over 3. So my polar form, I have run out of room, so I'm going to put it up here. The polar form will be 2 square root of 3 cis 4 pi over 3. It takes a little bit longer to write a number in trig form than it does to go from trig form to standard form. Okay, let's write this one in reduced standard form. Alright, so we've got two things going on here. I have the product of two polar forms, trig forms. So I'm going to write this as 2 times, I'm going to change these to standard form. So cosine of 5 pi over 6 is negative square root 3 over 2 plus I sine of 5 pi over 6. Sine of pi over 6 is a half. I'm going to write my I there because that is what that I is. And then I'm multiplying that by cis of 4 pi over 3. So cosine of 4 pi over 3 is a negative 1/2. It's down there in quadrant 3. Plus I sine of 4 pi over 3 is a negative square root 3 over 2. And then I don't forget my I, because that's what that I means. Now I need to write it in reduced standard form, so I'm going to multiply this out. I have 10 times, okay, negative square root 3 over 2 times negative 1/2 is a positive square root 3 over 2, over 4. Multiply the numerators, multiply the denominators. Negative square root 3 over 2 times a negative square root 3 over 2 I will be a positive 3/4 I. 1/2 I times negative 1/2 is a negative 1/4 I. And then 1/2 I times a negative square root of 3 over 2 I is a negative square root 3 over 4 I squared. Once again, I have that I squared that's going to change this sign to a positive. I have 10 times square root 3 over 4. I'm going to combine these two I terms. Okay, that'll be positive 2/4 I, which is positive 1/2 I. And then here I have a plus square root 3 over 4. Almost there. Okay, square root 3 over 4 plus square root 3 over 4 is 2 square root 3 over 4, which is square root 3 over 2 plus 1/2 I, multiply through by your 10, and you get 5 square root 3 plus 5I. And that is reduced standard form, A plus BI. Okay, that is it for today's lesson. 20 minutes. That's a good day for a first day of a unit.